chemistry students. This is Dr. Tullis. We are moving on to the next chapter, which is about electron transfer reactions, and we are going to learn about electrochemistry. Why study electrochemistry? It helps us to understand batteries, corrosion, industrial production of chemicals like chlorine, sodium hydroxide, fluorine, aluminum. There's biological redox reactions and electron transfer reactions that are known as oxidation reduction reactions or redox reactions. Redox reactions can result in the generation of an electric current or be caused by imposing an electric current. The force with which electrons travel from the oxidation half reaction to the reduction half reaction is measured as voltage. You've probably heard that term before. Therefore, this field of chemistry is often called electrochemistry. We're first going to look at how to balance equations for oxidation reduction reactions in acidic or basic conditions using the half reaction approach. Electrochemistry is the field of chemistry that studies chemical reactions that produce or are caused by electrical energy. Because all electrochemical reactions are oxidation reduction reactions or redox reactions, we begin our exploration of this subject by first describing electron transfer reactions in more detail. So in this chapter, we will show how a cell is constructed to physically separate an oxidation reduction reaction into two half reactions. Here's a picture of the oxidation of copper wire in a solution of silver nitrate. And we can see that it leads to the growth of silver crystals on that copper wire. Here's a review of terminology. If something is oxidized, it is losing electrons and it has an increase in oxidation number. You might remember from Gen Chem 1, Leo the lion goes grr. Or you might remember oil rig. The loss of electrons is oxidation. That's what that stands for, the Leo. Or we can say oxidation is losing electrons. In oxidation, we are becoming more positive. A reduction gains electrons. So gaining electrons is reduction. And we have a decrease in oxidation number. So we're becoming more negative, or reduction is gaining electrons. If you gain electrons, electrons are negatively charged, you become more negative. The oxidizing agent, or it might be called the oxidant, is the one that is reduced. And the reducing agent, or the reductant, is the one that's oxidized. It is the electron donor. The oxidizing agent, again, is the one that is reduced. And when I say the one that's reduced, it's the whole species that's reduced. Let's review how to assign oxidation numbers. The sum of all oxidation numbers of a molecule or ion is equal to its net charge. For example, if I have hydroxide, OH, with a -1 charge, I'm going to go down to where it says oxygen is usually a -2. So I'm going to give that a -2 value. And hydrogen usually is a +1. A -2 plus a +1 is -1, which is good because OH has a -1 charge. The oxidation numbers of atoms in the uncombined element is 0. If I just had aluminum, its oxidation number is 0. If I have H2, its oxidation number is 0. Everybody in group 1A will become a +1 in compounds. Everybody in 2A will become a +2 in compounds. For example, if I said lithium chloride, Li, lithium, is going to be a +1 because it's in my first group. If I had calcium chloride, CaCl2, calcium is going to be a +2. We know that because there's 2 chlorines that had to have come from that charge. Fluorine is always -1 in compounds. Oxygen usually is -2. Here's another little visual summarizing everything we just said. In Gen Chem 1, we did a brief introduction on the concept of the half reaction method for balancing simple oxidation reduction reactions. Redox reactions always involve a transfer of electrons from one species to another. The species losing electrons is oxidized. The species that gains electrons is reduced. Again, if it is reduced, it is the oxidizing agent. If it is oxidized, It is the reducing agent. All redox reactions must balance. And when I mean balance, it needs to balance mass and it needs to balance charge. Let's look at a redox reaction here. I have solid iron plus copper ions that are in aqueous solution, and it yields Fe plus 2, so iron ions in aqueous solution and solid copper metal. Let's look at the difference going from left to right for my iron. Iron, in its natural state, has an oxidation number of 0. And notice over here, its charge that it's given is its oxidation number. So I went from 0 to plus 2. That means I lost 2 electrons and I became more positive. Therefore, it's been oxidized. So iron, we can say, is oxidized. Therefore, it's also the reducing agent. Then let's look at copper. Copper over here has a plus 2 charge. Copper by itself is 0. Going from plus 2 to 0 is becoming more negative. It's gained 2 electrons, so this copper plus 2 has undergone reduction. That copper plus 2, therefore, is the oxidizing agent. Remember, ask yourself, who became more positive? They are oxidized. Who became more negative? They are reduced. Here's an example of a redox reaction. I've got solid copper plus silver ions, and going from solid copper to copper plus 2. Again, if it's solid copper, it has an oxidation number of 0. 0 to plus 2, it became more positive, so it's been oxidized. Silver plus 1 ions to go to silver metal, which is 0, it's become more negative, so it's been reduced. Here is our copper metal placed in that silver nitrate solution, so we have Ag plus ions. And with time, that copper reduces the Ag. If this is being oxidized, it is the reduction agent. So that copper is the reducing agent to reduce that Ag plus ions. We can see the blue color of the solution is due to the presence of aqueous copper ions. Notice that's one of our products. And all of these chunks, we can see all of these crystals that are formed are our silver crystals on that copper wire. When a reaction has been determined to involve oxidation and reduction by noting that oxidation state changes have occurred, the equation is separated into 2 half reactions, which are then balanced for mass and charge. So I'm going to look at a reaction. First thing I'm going to do is assign oxidation numbers. Solid zinc is 0. Ag is already given a plus 1. Zinc is already given a plus 2. And solid silver a 0. Let's look and see if anything has changed. Oh yeah, zinc went from 0 to plus 2. And silver went from plus 1 to 0. Zinc became more positive. It's been oxidized. Silver went from plus 1 to 0. It's been reduced. I'm going to separate into my 2 half reactions. The zinc that's been oxidized, let's write that reaction. So I'm going to write zinc solid, arrow, zinc 2 plus, AQ. So I've got that piece. The second, the reduction, I'm going to write Ag plus on the left, right there, arrow, Ag solid on the right. That's my reduction half reaction. The next thing I need to do when I look at just my zinc solid and my zinc plus 2, there's 1 zinc on the left and 1 zinc on the right, so I'm balanced for mass. But I'm not balanced for charges. On the right, I have plus 2, and on the left, I have 0. So I need to make the right side 0, and to do that, I can just add 2 electrons, because this is telling me it's a plus 2, so a plus 2 and a minus 2 gives me 0. Down in the silver, I can say, okay, I've got Ag plus and Ag. So I'm balanced with silver, but let's look at the electron. I have a plus 1, so let's make a minus 1. Pretend that this doesn't exist right now. So I need an electron. So 1 electron and a plus 1 charge gets me a neutral compound. I'm going to rewrite this because that's a little messy. But then we need to look at the number of electrons in both of those half-lives. The number of electrons lost in the oxidation half reaction must equal the number gained in the reduction. Notice that I lost 2 electrons on the right. If you lose, that means that they're in the products. I gained 1 electron and it's in the reactant for the reduction half, but they need to be the same. So I can multiply everything in my second part by 2 to get this 1 electron to be 2, but I have to do it for every species. So I just rewrote it here. To get my 1 electron in the reactant to equal the 2 electrons that are here in the product, I need to multiply everything by 2. So that would give me 2 Ag pluses, 2 electrons, and 2 Ag solids. Then the next part, we add the 2 half reactions together and the electrons will cancel. Notice that on the right side of my arrow I have 2 electrons, and on the left side of the second equation I have 2 electrons. They cancel out, and then I just bring everything else down. So I bring down my zinc, I bring down my 2 Ag plus, that's everything on the left side. On the right side I bring down the zinc plus 2 and the 2 Ag solids on the right. That yields a balanced oxidation reduction reaction. Let's look at another reaction. Here I have copper ions in solution plus aluminum to yield solid copper and aluminum ions in solution. So I'm going to match together my copper and copper, my aluminum and aluminum. Copper plus 2 to solid copper is 0. So I am becoming more negative. That must be reduced. My aluminum went from 0 to plus 3. It's been oxidized. It's become more positive. Let's write our 2 half reactions. I've got copper plus 2 yielding copper solid. I have 1 copper on both sides, but my charges are not balanced. If I have plus 2, I need 2 electrons to make that equal the right side. Let's look at my aluminum. I have aluminum, solid, arrow to aluminum plus 3. Well, if I have a plus 3 on the right, I need a negative 3, or 3 electrons to balance the left. There we go. So we have our reduction half-life and our oxidation half-life. The reduction is the copper, the oxidation is the aluminum. The next thing we need to do is make sure that when we combine these, our electrons cancel out. Here I have 2 electrons on the left. Here I have 3 electrons on the right. We need to get them to be the same. The first common multiple that they have in common is 6. So let's get both of them to 6. I'm going to multiply the top by 3. I'm going to multiply everything on the bottom by 2. That would give me 3 copper plus 2 ions plus 6 electrons to give me 3 solid coppers. And on the bottom I'm going to have 2 aluminums yielding 2 Al plus 3s and 6 electrons. There's the neater version. And then we can see that our 6 electrons and 6 electrons will cancel out, leaving me with a net ionic equation of bringing everything down. My 3 copper plus 2s, my 2 aluminum solids, that's the only thing on the left. And on the right, I'm going to have 2 Al3 pluses and 3 solid coppers. That's our net ionic equation. We are now balanced for mass and charge. When balancing equations for redox reactions that are in aqueous solutions, it's sometimes necessary to add water molecules and either H plus in acidic solutions or OH minus in basic solutions to the equation. Here's the method if we are looking at acidic solutions. We will do the same. Number 1, divide the equation into half reactions. We've already done that. We're going to 2, balance atoms, every atom other than hydrogen and oxygen. Number 3, then we're going to balance the oxygen atoms by adding water. Then we're going to balance the hydrogen atoms by adding H pluses. Then we will balance the net charge by adding electrons wherever we need to. Then we'll make electrons gain and loss in each half reaction equal. Then add the half reactions together, cancel any species that occur on both sides, and reduce the coefficients to the smallest whole numbers. I know that's a lot to think about. Let's look at a few more rules before we do this practice problem. Never add O2 when we need to add oxygens. Don't add just O, and don't add O2 minus to balance oxygen. Remember, when I need to balance oxygen, we add a water. If I need hydrogens on one side, don't ever add H2 or just H to balance the hydrogens. We would add H plus. Make sure you write the correct charges on all ions, and then check your work to make sure that the mass and charges are balanced. I know this seems like a lot. How are you going to master balancing? You need to practice, 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 practice. So let's look at this first one. Balance the net ionic equation for the reaction with VO2 plus with zinc in acid solution. So you will be told if it's an acid solution or if it's a basic solution or if it's neither. So we're told acidic solution, and we're given our VO2 plus zinc yielding VO2 plus and zinc 2 plus. The first thing I did was write it out, and I assigned oxidation numbers. The zinc was easy because it's 0, and over here my zinc was 2 plus. So going from 0 to 2 plus, it became more positive, so it's oxidized. Now this VO2 plus, I had to assign oxidation numbers. And look back at those rules. Oxygen is always -2. So if I have 2 minus 2's, for that half of that compound, that's a -4. Now, let's look at what V is. -4 plus what is equal to, this whole compound has a +1 charge. Well, that's got to be a +5. That V is a +5 oxidation number. And then on the right, I just have VO2 plus. Okay, O is a 2 minus. So what minus 2 is +2? Well, that's got to be 4, +4. So my O stayed the same, but the V went from +5 to +4. It got smaller. So this species was reduced. Next, I'm going to write out my half reactions. My oxidation was zinc solid to zinc +2. And notice that I added the 2 electrons on the right because this is +2, so I need a -2 or 2 electrons to equal my neutral zinc on the left. Then I have VO2 plus on the left and VO2 plus on the right. Well, we said to balance everything but the oxygens first. So here on the left I have 1V and here I have 1V. Great. Next, let's look at the oxygens. On the left, I have 2 oxygens. On the right, I only have 1 oxygen. So I need 1 more oxygen on the right. But you can't just add an O. We have to add an H2O. So I'm going to bring down my VO2 plus. I'm going to bring down my VO2 plus. I'm going to add a water. So now I have 1V, 2 O's, 1 O, and 1 O is 2 O's. Now notice that on the right, I have 2 hydrogens. So I need 2 hydrogens on the left. That means I'm going to add 2 H pluses. Adding 2 H pluses then gives me 2 H's on the left, 2 H's on the right, 1, 2 O's on the left, 1, 2 O's on the right, 1 V, and 1 V. Everything is balanced now except charge. Let's look at our total charge. I have 2 positives, another positive, so that's 3 positives, and I have 2 on the right. That means I need to add 1 electron to the left so that I can have a +2 on the left and a +2 on the right. Great! We are even balanced for charge. Now I want to look at my oxidation. See, I have 2 electrons on the right, and on the reduction I have 1 electron on the left, so I need to multiply everything by 2. When I bring that 2 to every one of these species, that gives me 2 electrons, 4 H pluses, 2 VO2 pluses, 2 VO2 pluses, and 2 waters. Now we combine both of those. We can see that our 2 electrons on both sides will cancel out. We bring everything else down, and that gives us our net ionic equation. Here's another example in acid solution. See if you can write this. Figure out the oxidizing agent, the reducing agent, who is oxidized, who is reduced, and knowing that's an acid solution, go through the same steps that we just went through in that last example. Let's see how you did. That MnO4, I needed to assign oxidation numbers to. The first easy part is the oxygen at -2. If I have 4 -2's, that oxygen has a whole -8 attached to it. -8 plus what gives me a -1 charge? That's got to be a +7 for that manganese. This one's an easy one. I like it when the ion's already labeled. Fe is a 2 plus. And on the right, the manganese is given as 2 plus and the iron is 3 plus. What happened to my manganese? It went from +7 to +2. It was reduced. My iron went from +2 to +3. It became more positive. It was oxidized. Let's write both of those half reactions. The oxidation, iron 2 plus to iron 3 plus. Right off the bat, I can see that my ions are balanced, but my charge isn't. I can get that 3 plus down to 2 plus if I add an electron, though, on the right. Let's look at the MnO4 minus reducing to Mn2 plus. I have 1 manganese each, but I notice that on the left I have 4 O's. Because it's an acidic solution, that means on the right I need to add 4 O's, which would be 4 waters. Now I notice that on the right I have 8 hydrogens, so I need 8 hydrogens on the left. And to get that, I would add 8 H pluses. Now let's do a charge check. On the right side, I only have +2. Let's look at the left side. I have 8 H pluses and 1 minus, so that would be +7. How do I get that down to +2? Well, I need to add 5 electrons to the left. Lastly, I go, oh, I've got 5 electrons on the left, 1 electron here. I need that 1 electron to be 5, so let's multiply everything in this top half by 5, giving me 5 Fe2 plus, and bringing down everything for my reduction half, and bringing down my 5 Fe3 plus, the manganese +2, and the 4 waters. And we crossed off those 5 electrons that were on both sides. Pause here to read a summary of balancing redox equations. What if we have to balance equations that are in basic solutions? So we have aluminum metal, we have Al, solid aluminum metal, is oxidized with water, and the products are this and that. It's a little bit messy, but you get the idea. When we have a basic solution, we're going to separate into our 2 half reactions, so we need to assign oxidation numbers and the whole thing. We need to balance it. Now, we will add OH minuses equal to the number of H pluses on both sides. And if H plus and OH minus are both on the same side of the equation, we combine them to form water. And if we have water on both sides, we're going to cancel the waters out. Now, sometimes you might find that there's 3 waters on the left and 2 waters on the right. So that would cancel down to just 1 water on the left. Let's do that sample problem. I assigned oxidation numbers to everybody, and I found that my aluminum went from 0 to +3. Check the oxidation numbers. I had 4 OHs. Each O is -2 and an H is +1, so that ends up being a -1, and there's 4 of them, so that's -4. The whole thing is a -1, so 3 minus 4 would be -1. That aluminum would be +3. So I write my oxidation half reaction, aluminum to the aluminum hydroxide with a -1. We can see that when I bring down the aluminum and I bring down that aluminum hydroxide, I have 1 aluminum and 1 aluminum. But notice that I have 4 OHs on the right. And because it's a basic solution, I need 4 OH minuses on the left. That now gives me a charge of 4 negatives on the left. Well, I already had 1 negative on the right, so I need 3 more negatives to balance out my charge. Now let's bring down the water and the hydrogen. When I add oxidation numbers, H2O, H is a +1, O is a -2, and over on the right, H2 is 0. So going from +1 to 0, that's our reduction half. I have 2 H's and 2 H's, so we're good. Notice that I have 1 O. Well, it's a basic solution, so on the right I need to add an OH. At first I only added the 1 OH because I only needed 1 more O. But when I added 1 OH, that then gave me 3 H's. On the left only have 2 H's. Well, if I put 2 OH's, that gives me 4 H's on the right. So then I need to add a 2 over here to give me 4 H's on the left. Double checking, I have 4 H's and 2 O's. 1, 2, 3, 4 H's and 2 O's. We're balanced as far as mass. Now let's check the charge. Because I have 2 OH minuses, that's a -2 on the right. So I need 2 negatives on the left. So we'll add 2 electrons on the left. If I have 2 electrons here and 3 electrons here, I need them to be 6. So I have to multiply everybody in the top by 2, everybody in the bottom by 3. When I do all of that distributing, check to see that you get the same 2 down here that I did, and then let's see what we can cancel out. 6 electrons on the right, 6 electrons on the left. 6 hydroxides on the right, 8 hydroxides on the left. So that 6 will cancel out, and we'll do 8 minus 6 to give me 2 hydroxides on the left overall for my net ionic equation. See if you can work through this one in a basic condition. Pause the video. Let's see how you did. My aluminum was oxidized. So when I brought down both of those, I had 1 aluminum each. So I noticed on the right I had 3 OHs. So I'm going to add 3 OH minuses on the left. That means I have 3 negatives on the left. So I need 3 negatives on the right. My sulfur was reduced. So I'm going to write my S producing HS minus. My S's are balanced, but I have an H that I need to account for. So on the left, I need to add an H plus. But remember, when we add an H plus, we also have to add an OH minus. And therefore, the H plus and the OH minus combine to form water. Now let's look at what we have. On the left, I have an S. On the right, I have an S. On the right, I have an H. On the left, I have 2 H's and an O. In order to balance that 1 hydroxide extra that I added, I need an OH on the right. What's my charge on the right? A negative and a negative is 2 negatives, so on the left, I need 2 electrons. I have 3 electrons here and 2 electrons here. Let's get them both to 6. When I do that and I bring everything down, I end up with 6 hydroxides on the left and 3 hydroxides on the right. And that can reduce down to 3 hydroxides on the left and none on the right. Double check to see how you did. Sometimes when you are balancing redox equations in basic solutions, it can be a little more challenging than balancing them in acidic solution. So rather than learning a separate method for balancing equations in basic solutions, some students find it easier to first balance an equation as if it were in acidic solution and then add enough hydroxide ions to both sides of the equation so that the H plus ions are converted to water. Let's look at how this works for balancing the reaction of the hypochlorite ion with manganese 4 oxide to form the chloride ion and permanganate ion. So I wrote the equation here. I assigned everybody their oxidation numbers, and then I was able to look at chlorine and see that it went from +1 to -1, so that one is being reduced. The manganese is going from +4 to +7, so it's been oxidized. I'm going to write out the reduction half reaction and the oxidation half reaction, and let's see what happens. ClO minus to Cl minus 1. I have 1 chlorine on both sides, but notice on the left I have 1 O. So pretending as if it was an acidic solution, on the right side I'm going to add an H2O to give me that extra O that I need on the right. That then gives me 2 hydrogens. So on the left, I need to add 2 H pluses. Here's where we make it a basic solution. Because I have 2 H pluses on the left, let's add 2 OH minuses on the left. And if I do it on the left, I have to do it on the right. The 2H and the 2 OHs turn into 2 waters. Let's look at our charge. On the right, I have a -1 and 2 minus ones, so that's a total of -3 on the right. So I need it to be -3 on the left. 2 plus ones and 2 minus ones, those cancel out as far as charge. So I only have 1 minus 1. I need 2 more negatives. Let's look at our oxidation. We have MnO2 and MnO4. On the left, I need 2 more O's. So I'm going to add 2 H2O's. That now gives me 4 H's on the left, so I need 4 H pluses on the right. And because I have 4 H pluses, let's add 4 OH minuses on both sides. Let's look at our total charge. On the right, I have 4 pluses and 4 minuses, so those are going to cancel out. So I only have 1 negative on the right. On the left, because of those 4 OHs, I have 4 negatives. So on the right, I need 3 more electrons. Because I have 2 electrons in the reduction half and 3 electrons in the oxidation half, I need them both to be 6. So I'm going to multiply everybody up here by 3, everybody down here by 2. Let's see what that gets us. This 3, when it distributes to everything, that's going to give me 6 electrons. This is 2 waters, so 2 times 3 is 6 waters. That'll be 3 ClO minuses, 3 Cl minuses, 3 waters, and 6 OHs. Down here in the oxidation half, that 2 is going to distribute to everybody, so that's going to give me 2 MnO2s right there. That's going to give me 4 waters right there. That's going to give me 2 MnO4s on the right, 6 electrons on the right, and I had 4 waters times 2 is 8 more waters. Then I'm going to do some combining. 6 electrons on the right, 6 electrons on the left, those are going to cancel. I had 6 waters here plus 4 waters is 10 waters on the left. On the right I had 8 waters plus 3 waters is 11 waters, and that should be all of my combining. Now let's find my net ionic equation. After bringing everything down, I'm going to look at my waters, 10 waters on the left and 11 waters on the right. The 10's going to go away, leaving me with just 1 water on the right. If I look at my hydroxides, I had 8 hydroxides on the left and 6 on the right. That 6 will go away and leave me with just 2 hydroxides on the left. And after bringing everything else down, we can see that this is my net ionic equation in basic solution. Notice I still have those hydroxides.